artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hello and welcome to episode 176. Today my guest is Bart Selman. Bart is professor of computer science at Cornell University, and he's been helping people understand the potential and limitations of AI for several decades, commenting on computer vision, self-driving vehicles, and autonomous weapons, among other technologies. He researches several topics in artificial intelligence and has co-authored over 100 papers, receiving a National Science Foundation Career Award and an Alfred P. Sloan Research Fellowship. He's a member of the American Association for Artificial Intelligence and a fellow of the American Association for the Advancement of Science. We'll be talking about the impact AI is having on our society as a whole, common sense, artificial general intelligence, computer vision, today's large language models and their impact on computer programming, and how much they might really be understanding. Bart will also give his take on how good they are, how to understand how they're working, and his experiments in getting ChatGPT to understand geometry. Just to explain a couple of things that will come up in the interview, I mentioned WordNet at one point, and that was a brain fart. I meant to say Word2Vec, which was a technology from 2013 that expanded the field of natural language processing by analyzing enough examples of text to understand relationships between words to the extent that it could model those relationships as vectors, and then you could do vector arithmetic on them. The end result of that would be that you could do a kind of algebra, like ask it what the result of king minus man plus woman was, and it would tell you queen. Another term that bears explaining is the mention of System 1 and System 2 thinking. These are terms that were invented by Daniel Kahneman, which you can read about in his book, Thinking, Fast and Slow. Briefly, System 1 thinking is intuitive pattern recognition, which we would recognize as instinct and actions that are driven by the reflexive part of our brain. System 2 thinking we would recognize as the application of conscious, logical, deliberate thought that might exercise implicit or explicit symbolic logic. Anyway, now enjoy the interview. Bart Selman, welcome to AI and You.
It's very good to be here. Thank you.
It is an amazing time for people who are interested in the impact of artificial intelligence on our society and how it intersects with people who wouldn't consider themselves technical, wouldn't normally have been involved in anything to do with technology, would have thought themselves outside of that sphere. And yet now we have large language models like ChatGPT that have been adopted by 100 million or more users at the moment. It's clearly mainstream. It's a South Park episode. It's all over the place. And you have been in this space of the impact of artificial intelligence and foreseeing that on us for quite some time. You were at Asilomar in 2009, which was a conference for doing that. I'd like to talk about some of that. But what do you want to say in general at the moment, to begin with, about where we stand with respect to how well we are doing collectively at anticipating and preparing for the impact of artificial intelligence on our society as a whole?
Yeah, so that's a good question. I think the good thing I'm seeing is that there is lots of discussion about the new AI capabilities. As a researcher in the field, I should stress that I've been in the field for several decades. We had the first breakthroughs were really in computer vision and audio recognition around 2010, 2012 with deep learning methods, learning very complex neural networks being trained on lots of data. But the most recent development around large language models has further accelerated our field, reaching milestones that experienced researchers thought were decades out. So, and scientifically, it's an exciting time because we see capabilities like reasoning, common sense reasoning capabilities, language understanding capabilities that we did not expect literally for another 20, 30 years. So that's quite an excitement. It does have implications for society in the sense of what impact will this have on the acceleration of technology? How do humans have to adapt? What are the risks? The good thing I see is that people are discussing these issues and people are becoming aware that we should have some policies in place or some regulations or at least some careful thought about how to move forward. I should say it's not so easy. These discussions, in my mind, have just started, and it will take quite a bit more work. But even informing the general public is important so that politicians and policymakers are serious about the implications.
And I'd like to talk about our role as computer scientists in locating where we are in terms of our progress on artificial intelligence according to any kind of scale that helps people understand how fast we're moving. If computer science should be good for anything, it should be good for quantifying and measuring and defining things like this. And yet, when we start talking about general intelligence, we're reduced to terms like common sense, which I always find just looping back on myself, like I can't see, I'm pointing the finger at myself. And this doesn't get me anywhere. And in the last year, we've seen this vaulting, this leapfrogging of capability that I still don't have the right terminology to explain to my satisfaction. So what sort of science is required or involved in helping people understand anything like, yes, we've just gone from a 55 to a 72 on a scale of artificial intelligence, not that that might necessarily be a good way of describing it, but anything that helps people understand how close we are to the next stage.
Yeah. So no, that's a very good question, and it's not so easy to explain. I think that a lot of people sort of struggle with what is really going on. And I've had other interviews where the question would come up and says, well, you guys always say that there's transformative things happening, but really, what does it mean and how transformative? So let me put it a bit in context. I think a good way to look at it is that we've seen breakthroughs in AI, let's say in computer vision and things like AlphaGo and AlphaZero, or these these top-playing programs that could beat human players, the best human chess player, then the best human Go player. And we see some breakthroughs in protein folding, a key challenge in biology and medicine, how do proteins fold. So we see those advances, and those are examples of what's called narrow AI. So these are very specific capabilities, and there's always a certain sense at the end of these achievements that, okay, maybe the humans are not the best at playing chess, but and machines can do that better. But it's not such a big issue. It's a very narrowly described domain or circumscribed domain. I would even say the same for computer vision. So computer vision is starting to make self-driving cars a possibility, and we're not quite there yet, but we're getting close. But you can even say computer vision is somewhat restricted cognitive capabilities. We know exactly, in particular, what it is to see, and we now have machines that can see as well as we do, and we can sort of live with that. What I think the language models bring, the large language models, is this certain shift where this feels more like a much more general kind of intelligence. So language is what allows us to communicate, to transmit ideas, to form scientific theories, to write textbooks, to write regular books, to communicate with each other and to capture ideas about our thoughts. It also allows us to make plans and set policies and do government and do law and do medicine. And the thing that I have to stress, and I stress to my students, is computers really could not understand language at all 2 years ago or a year ago. The language understanding capabilities were very limited. And I teach computer science, and I emphasize it. I illustrate it by saying, look, we train computer scientists to write programs, to code. And one of their main tasks in an organization was to take a language description of what a user wants and write that into a programming language like Python. That translation between a natural language like English and a formal language like Python was a very human activity, and it was very hard to automate. And we actually there's about 15 years of work on automated programming, trying to do that automatically. The bottleneck always was understanding the language. We could not. And so the large language models is the first time that we actually now have systems that understand language. Now, there's some debate on how deep and how real the understanding is, but there's a significant group of computer scientists, including myself, are quite convinced that the understanding is much deeper than we would have thought. So they actually do understand text to a remarkable level, let's say at the level of a college student. And what that means is now suddenly the machine can read all the textbooks. It can read all the policy papers. It can read all the legal documents and understand them and generate answers. You can ask questions about these texts. So I encourage my students to look at, for example, something like ChatGPT, not as a chatbot, because as a chatbots have been around and they're sort of, you can sort of think of them as how they mimic speech. No, I encourage my students to treat ChatGPT and GPT-4, and you have to go to the latest models really, as a knowledge source, as a very experienced tutor, as in some sense having access to a professor that you can ask in the middle of the night about the question you have. And I've done this myself in all kinds of topics, computer science, physics, mathematics, philosophy, and I'm extremely impressed with the answers and the quality of the answers I get. And I do it specifically in domains that I know about. So I know that the answers are coherent and shed new light on the topic. So it's that level of understanding that it's hard to explain to a non-computer scientist why natural language understanding was a hard problem. So you sort of have to accept that computers just couldn't. And we didn't know how to do it for 50, 60 years. That's why we had computer programmers write code. The human took the language and then wrote the formal language. Suddenly, we have these large language models that can do it for us, write code, and understand the language. So it is a dramatic change in AI capabilities, and it's this shift from very specialized systems like that can play Go, that can play chess, to these very general systems. I can ask it about thousands of different topics at a college level of knowledge. So it's a whole new entity and much more like a human intelligence than we've ever seen before.
Right. I provided my daughters, by the way, with directions regarding the use of ChatGPT that were exactly parallel to what you gave your students, and I agree with that. I want to pick up on the word that you've used more than any other so far, which is understanding, because that is pivotal. And I've been frustrated that for the last several years, my understanding of what the word understanding means has gone down. And with respect to these large language models, as a computer scientist, I understand what it means to be predicting the next most likely word using algorithms that start with things like Markov chains and progress through technologies like WordNet and get more and more complicated. It is still not, for me, an adequate explanation of how good they are now. The fact that it could construct computer code, software, that was syntactically correct, I could buy. The fact that it is semantically correct and tracks the variable names through function calls, that seems to me far beyond what it says on the lid, that this is how this is constructed. And I have been talking about emergent phenomena for a decade, so you'd think that I should be able to be comfortable with that when confronted with something like this, but I don't know. Is this shockingly good performance? Well, is it shocking to you, and is it explained as an emergent phenomena, or do you have anything else to help connect the dots here?
Yeah, let me give that a try. So first of all, it was a huge surprise to me, surprise. So I actually taught a course, my AI course, Foundation of AI course, in the fall of 2022. And we did quite a few questions, homework questions, where we showed the limitations of, I guess this was GPT 3.0. And you could come up with all kinds of little reasoning questions and something as simple as the suitcase did not fit into the trunk of the car because it was too big. And what does the it refer to? Well, it refers to the suitcase. So, but you could show that GPT-3 had no clue and it would just randomly guess. So we were quite convinced that no, it had no real understanding. It was doing this statistical modeling, but it didn't lead to any real understanding. What happened is 3.5 came out, GPT 3.5, GPT-4, and suddenly all these queries that we had to demonstrate how it did not understand language flipped around and showed, no, it does understand the concept. What I think is confusing to people is that this notion that it's just predicting the most likely next word is the full story. In the sense, it's technically what it's doing. But what we sort of miss, and actually the colleague Lillian, Professor Lillian Lee, who pointed that out to me, is to be able to make these good predictions of the next word, it has to construct internally in its billion parameter model very good approximations and abstractions of concepts. So basically it has to find out, a good example was a good article actually in the New Yorker about compressing the content of Wikipedia. So if you think about Wikipedia and if you want to store it and then recover it literally, there are very well-known compression techniques, and the lossless compression techniques will give you the exact text back. What GPT-4 does is it doesn't compress the text that way. It abstracts higher level concepts of an article. So let's say I want to write an article on Newton's laws. I could write an article on Newton's law that is reasonably good. It would not have any words that are identical to the current article in Wikipedia. I haven't even read the article on Wikipedia on Newton's law, but I would use my higher level notions and understanding of Newton's laws, actions, reaction, and those kind of things, and come up with an article that in content is a reasonable representation of what is in Wikipedia. And that's exactly what ChatGPT does. It builds these higher level representations of concepts and uses then these higher level abstractions to generate coherent text, fill in details with coherent language. But that language is not a recollection of what it has seen before. It might never have seen actually that article. It will still generate a reasonable article. Now, what is a big surprise is that it could do that it could actually find these higher level concepts. Presumably, these are similar to the concepts we form in our own brain, how we connect words and how we abstract away information. When we read an article, we abstract only key concept, not key words, key concepts behind the article. And that's the way we understand text. So that similar kind of understanding is occurring inside GPT-4. And it is obtained by training this model to predict the next word. But that's sort of a side issue. It is you call it an emergent effect, the understanding, the higher level concepts that are formed inside the network, those are emergent. And those are emergent from the training regime. So by forcing it to try to predict the next word, it can only do that if it develops the right higher level concepts. And the surprise, I think, to almost every researcher or a lot of AI researchers is that this would emerge, that these concepts would emerge in that way. I used to talk about, for example, Google Translate. Google Translate, you can show, has all kinds of, doesn't understand language very well. And so I said, that's just more a statistical trick. It's doing a translation by a pattern matching kind of thing. It knows French language and an English sense, and it does a fancy form of pattern matching. GPT-4 is quite a different beast. It has the right abstractions. Now, for a person that looked at language learning before large language models, it's very odd because the general sense was, we can only learn a language just like a child learns a language by interacting with the world, by observing objects, seeing tables, seeing books, and moving things around, walking around. Basically, it's called grounded language. So the idea was the only way to get at semantics is to use our other perceptual inputs, touch and motion and vision, that somehow you had to see the world to do that. Of course, a total surprise is that the same kind of semantic relationship and higher level concept can be obtained by just seeing the text. And the only parallel I sometimes give to my students is, well, if you think about actually a blind person, somebody born blind, actually also can get a conceptual understanding of the world while never having seen the world. So maybe indeed, as these models show, is you can get a semantic understanding of words by just looking at relations between them, and apparently by just being forced to predict the likely next word. But saying it's about predicting it misses the point.
And it's not just text now. They have in ChatGPT, if you have the subscription model, then it has a staggeringly good general machine vision capability for recognizing images. But maybe human intelligence isn't as ineffable as we thought. Maybe all I'm doing is just coming up with the most likely next word when I'm speaking. I want to hold your feet to the fire a little on something that you mentioned a lot there, which was that it forms these concepts, and that you asserted that we can tell that it's doing that. How can we tell that? Is there a way of mapping it, or of generating information at the level of concept that tells us that it's done that?
I think there are some experiments trying to isolate that and really show it's there. It's also, to me, a little bit like it has to be there to do it, I guess. So that it sounds like strange, but if you think about, let's say, and this is back to this, what we call lossy compression. So basically, you take Wikipedia and you want to compress it, but you don't care about the details. You want to get the main ideas compressed right. So to do that kind of lossy compression, it seems that you need the higher level concept and the right higher level concepts. Now, could it do it in some totally different way? Possibly. It seems quite unlikely to me. The understanding is almost too good to be like that. You mentioned images. I think the nice thing, what we're seeing is the internal representation of images of what a table is and what a car is, and the language representations, the internal representation may be very similar. So our brain might just fluently merge them together. And so that's why you can link the different modalities together. So these higher level representations might all be shared somewhere in the brain. So that's our current sort of feeling. I should mention one more thing that I think is interesting. The next word prediction, there is, of course, the buffer. So it has this input buffer. So I've done experiments where it can actually use its own buffer. So like one thing that people show is, okay, let's say I want to do a certain calculation, and I was just recently doing an experiment. So you can actually describe the sequence of numbers. And I said, consider adding 100 plus 101 plus 103 plus 106. I space them increasingly far apart. Now, you can then ask and add up that sum. So you describe that sequence and you say, add up that sequence. Now, if you ask it, okay, give me the result after adding 50 terms like that, you will get the wrong answer. It will try to come up in some sense with the next word, but it's not good enough to do that. So it gets the wrong answer. But then you say, okay, you have trouble doing this whole calculation in your head, but you have your own buffer. So now write down step by step this summation. Okay, so you don't give me the final answer right away, but you write the 50 intermediate sums down. And so you can look at your own buffer in some sense. And every time you take a step, double check it and make sure that it's right by typing checked behind that step. And you do it that way, and it will give you the right answer. So after 50 steps. So it predicts the next word, but it uses that buffer to come up with very coherent kind of statements. And it can do very long, it's like the working memory in the human brain. So it can steer in all kinds of directions. That's, for example, the same way it does Python code. It generates codes, but one character, one statement at a time, but conditioned, as we like to say, on all the previous statements. So that's why it can create coherent Python code, is because it has done 40 other Python statements before. So it's that combination of the current context and predicting what's next that makes it so powerful. And it's a very interesting form of machine learning and reasoning combined, because normally in machine learning, you would have inputs like pixels, like an image, and you would give it a label, cat, dog, car, etc. So the input space was completely different from the output space. In a large language model, the input space are tokens in a buffer, and the output space is a token. So it can put that output back into the input. And so it can actually do a level of recursion that appears to be sort of key to its power. But maybe that's the same thing for humans. We use language to think, And we actually, in our brain, generate language and reflect on the language. So we might literally be reproducing, one conjecture, we reproduce roughly the same way humans generate language. And humans generate thought.
And one of the ways that people have traditionally tripped up these large language models is by giving them math problems, which if they're not the kind that they've seen a lot of, they guess and get them wrong. But it seems to me, just from looking at what goes on in my own thoughts, that I don't use the same kind of intelligence to solve math problems that I do to do the System 1 type thinking of, that's a cat, what's a synonym for crimson, there's Bart, what did he just say? That pattern matching connectionist kind of intelligence. Instead, invoke principles and logic and symbols and process things in the way that computers have been very good at, and obviously could solve those math problems very easily. So if the large language model can tell that it's time to haul out that tool, well, that's easy. It just needs to know when that's needed and to transition from the mode of making stuff up. And we're seeing sort of some inroads in that respect. What do you think about this notion that there are these different types of intelligence that are appropriate to different contexts, and how much of the success of artificial intelligence for general purpose will hinge on being able to switch to the right one?
Yeah. So, no, that's a very good point. And I like the distinction between System 1 and System 2 thinking. System 1 being the quick pattern recognition driven system, and System 2, the more deliberative system. I think so. You raise an excellent point that one way to deal with things like calculation, actually, a colleague of mine did exactly that. So he actually he wrote a little script that basically you could tell ChatGPT, if you have to do a calculation, just put it between two keywords. When I see those keywords, I'll call a calculator program, or I'll call a Python compiler and run a piece of code. So you can actually merge the two paradigms by giving ChatGPT access to these other tools. So that's one very feasible way of dealing with things like calculations and logical reasoning. Personally, I'm also excited about this other form that I just described. If you actually use that input buffer, and I look at the input buffer as sort of a working memory, and you ask it to do the calculation using that working memory, then actually it can follow logical reasoning steps. So that really surprised me, but it's actually surprisingly good at it. So I would not be surprised. And this is, again, the power of language. So much can be described in language that if you can manage language well, you can be remarkably effective. Probably the best example I did is just a few weeks ago. This was before they incorporated images. I wanted ChatGPT to think about, there's a problem in mathematics that is, can you tile an infinite planar surface with certain kinds of tiles and like in certain shapes of rectangles and triangles and things like that. So there's a sort of an open mathematical conjecture of whether you could tile in a certain way and not in another way. And it was all about these tile shapes. And the way I would think about these problems, I would draw little triangles and rotate them a little bit and make them a little bit non-triangle and like distort them a bit. And you can sort of think about it visually and answer some of the questions that come up. But then I asked ChatGPT, I said, well, you've never seen a triangle because you can't really see. But what would happen if I would slightly distort this angle? And it will give the perfect answer. It would say, no, you can't tile this plane anymore with those kind of tiles. And then I said, how do you know that? He said, well, I've never seen a triangle or a rectangle or a straight angle, but I know enough about all the properties. I've heard enough about properties of triangles and rectangles so that I can use my language facility to think about it and give you the right answer. So it shows to me like the language, even spatial descriptions, and just having never seen anything, spatial descriptions, the language is a universal representation formalism. So that's, to me, is part of the power of these language models, that there's certain things that are hard to capture in languages, but so much can be captured in a language. These capabilities, I imagine, will keep growing further and further. So although I think that we will definitely see the use of adding the tools to the language models that they can call special tools, I think the capability of the language model will still also grow because language is such a powerful formalism. So, yeah.
And somewhere it's intersecting with the language of images because I've seen where you can post an image of something to one of these models and say, why is this funny? And it will explain the joke.
Yeah.
That is staggering. That is far beyond where we were before in terms of image tagging, which was fragile to the extent that it would tell you that a picture was of sheep, even when there were no sheep or any other animals in the image, but because it was a landscape and sheep were usually in landscape. And that was what it had learned to recognize. And this is far beyond that. So, I mean, it's very encouraging. That's the end of the first half of the interview. The rest will be next week in the interest of keeping the podcasts reasonably digestible. I have such an enjoyable time interviewing someone like Bart, who is such a deep thinker and excited about and by his own thinking. He opened up for me some new territory around the whole question of whether AI is really understanding. In today's news, ripped from the headlines about AI, whenever I talk about AI performing creative tasks with people, it's often deeply disturbing to them to contemplate such a thing. And if you're in that category, you're not going to like what comes next. A study from the Wharton School at the University of Pennsylvania focused on comparing a set of human-generated business ideas against those produced by machines. Their hypothesis was that to, quote, achieve high variability in quality and high productivity, most research on ideation and brainstorming recommend enhancing performance by generating many ideas while postponing evaluation or judgment of ideas. This is hard for human ideators to do, but LLMs are designed to do exactly this. End quote. So they fed GPT-4 a prompt telling it that it was a creative entrepreneur looking to generate new product ideas. And then they evaluated the quality of its ideas compared to an equal number of ideas generated by humans in a blind online test. This enabled them to rank the 400 total ideas, and in the top 40 of them, 35 were generated by GPT-4. And I don't need to tell you how much faster it was than the humans. Also, a study published recently in the journal Nature by Norwegian and Finnish researchers demonstrated that chatbots were better than average humans at generating novel ideas in the form of unusual or creative uses for everyday objects. So bottom line, I would say that if your security and your identity as a human depends upon your species maintaining an unassailable lead in creativity, then your future satisfaction will require re-examining that stand. Next week, we'll conclude the interview with Bart Selman when we'll talk about self-driving cars, the capability of large language models to synthesize knowledge across many human domains, Richard Feynman, Bertrand Russell, and much more. That's next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.